So if we look at if you look at the textbooks on machines, then so machine textbooks often start by describing magnet characteristics by B is equal to mu naught mu r h plus BR. And this assumes a linear relationship. So BR would be the residual magnetic flux density, and mu r is the relative permeability. And so if we might have a plot like this. So this is an example. We have B and H, and we might have some different curves for different temperatures. So this is actually for a Hitachi NMF 12G magnet, and this is at minus 40 degrees Celsius. This is 20 Celsius, and this is 160 Celsius. And the values on these values here are the BR values, the residual magnetic flux density values, and so they're different for different temperatures. And you can see that, so BR is a positive, and then we have H, that H along here, which is negative, and that gives you the relationship between the magnetic flux density in the magnet material and the magnetic field intensity H in the material. And remember that for a magnetic, as we discussed previously, for a magnetic circuit, you can think of, if you, for a regular magnetic circuit without magnets, we talked about this before, if we have a BH, we could change the B into B times A, which would be flux, and HL equals Ni around a magnetic circuit. So you can think of H as being related to Ni over the length of the magnetic circuit. So you can see that H is going to be proportional to some current. But this is for, so you can think of H as being related to current and B being related to flux. But this is a bit simplistic now, because you could have magnets involved too. But so this is often written in electromagnetic machine books. But then if you go and look at an electromagnetics textbook, you don't see this relationship written down for magnet materials. In electromagnetics textbooks, so most EM textbooks, they describe the magnetic flux density, not as written here in equation 1. This is often a starting point in the machines book. They describe it using magnetic flux density in a magnet. They describe the magnetic field as like this, and these are in general can be vectors, and m being a vector is what we wrote out when we were looking at the field equations. You know, we had del squared A is equal to mu naught J plus del cross M, where M was a vector. And we used this equation here. Now I'm going to talk more about machines and their application. So we're not going to look at it in terms of a vector, we're going to look at it as a scalar term. It would be in a magnetic circuit, for example. It's just going to have, we can assume that it has a 1 value going around a path. And so but if we look at this here, so this is the magnetic field intensity, and this is the magnetization vector. If we look at 2 and 1, they do look rather different. You know, this has got an H and then a mu naught here, but then we've got a mu naught mu RH here. It's rather confusing, I think. So I wanted to spend a brief bit of time discussing how they relate, and I think it's helpful to do that using magnetization versus field intensity plot. So looking at this equation here, what this is saying here is if we, and again I'll just get rid of the vector, we're just going to look at a scalar. So if we have some magnetization, if we apply a large enough H here, we should be able to change the magnetization of the magnet. So we can describe that by making some plots of how M and H change. So let me write that. So by applying a sufficient H field, the magnetic material can be reversed in magnetization direction. This can be described by a BH, well, not a BH, by an MH curve. So this is a BH curve here. So I want to explain how the BH curve can be obtained from the MH curve. MH and BH curves. So let's take the idealized case first. So idealized Okay, so make sure you have space to put two plots. So if we, let me draw this first. So here on the y-axis we have M, and on the x-axis we have H. And then, so in this example here, let's assume that the magnet, we have some magnet material. We could have a magnetic circuit. I'm going to talk more about the magnetic circuits. So we're looking at the magnet in a magnetic circuit, and by applying the H here, to apply an H field, we need to apply current, right? Field intensity. So that will then create some magnetic field intensity in the magnet. So this is just looking at the magnet. So the magnet has some magnetization vector M. Okay? And in this idealized case, M can only have one of two values. So this is M saturated, and this would be this is M saturated, and then this is negative M saturated. So assuming we start off having the magnet magnetized positively, then if we apply a field in the negative direction, then the magnet can stay magnetized until we get to this point here on the H, and that's called the intrinsic coercivity. So this is HCI. So M sat is the saturation magnetization. Spelled with a Z in America and an S in the rest of the English-speaking world. Well, maybe maybe except for Canada. We don't need to count Canada. And then HCI is the I said that's the intrinsic coercivity. Okay, so on this, we apply a field, and at this point, at this HCI, it changes direction. So we've flipped the magnetization direction. If we keep applying more negative, then it will just keep moving out here, and it won't change. And then if we apply a field in the opposite direction, when we get to plus HCI, then the magnetization direction will flip again. Okay. So that's the M. That's the magnetization vector. Now but then we know that B is equal to mu naught H plus mu naught M. Okay. So then now let's plot how B B and H are so if H is 0 here, if H is 0, then the magnetic field present in the magnet is going to be in the magnetic device it's going to be just equal to mu naught m. So then in the magnet, so then we have we can put that as BR, where BR, let me rewrite that, B is equal to mu naught H plus BR, where BR is equal to mu naught M saturated. In this example, in this idealized case. Okay, so then now if we're applying a negative H now, then we have this as a constant. So between here and here, the M doesn't change. Right? M is a constant. M constant. Okay? So then, if this is constant, then we're applying an H, a negative H, then B is going to go down linearly. And so then, actually I need to move this down here. And so now we apply an H. I'm going to move it down further, sorry. I should have made it bigger. So we reduce down, we apply an H here, this is H, and this is B now. And we start at BR, and we have a negative, we now apply a H in the negative direction by using a current, right? And so then we get to this crossing here. This point here is where the B field is 0. So that's called HC, the magnetic field intensity coercivity. But when we hit this point here, this is HCI, right? This is where the magnetization vector flips. And so rather than pointing, it flips directions. So it's rather than pointing positive, it's pointing negative. And so now this shoots down to below, and then we start. Now, if we start taking off the magnetization, then we move up on this alternative path here. And then again, if we hit the point where we're at HCI, it flips again, and we move up. We move back up. Do you see that? Can you see that okay? So this is the BH curve, and this part here is linear. That we're going down here. It's a linear path going down until we hit the HCI, intrinsic coercivity, and then it becomes nonlinear. Okay, does that make sense? Now the thing is, though, if you look at this HCI here is past where this HC hits. So if we had if our magnetization MH curve had a much higher M than HCI, then the load line, sorry, not the load line, the BH line here would cross before it wouldn't hit the zero, being linear. It would stop earlier than that. Maybe I'll draw that to show you. So if we have and this is an idealized curve. If we had an MH curve that looks something like this, so now this is a lot more narrow. It's not the HCI is not greater than the M. This is HCI. This is the M. So then we're going to have a BH curve that looks nonlinear. So we could start here, and it would come down, and then it would hit the point where the magnetization flips, and so it hasn't reached the B equals 0 point. It's hit the intrinsic coercivity before that, and so it flips paths. That's not symmetric. It's supposed to be symmetric. So this would be, if it kept going down to here, then you can see if you travel down this path, it would be linear all the way along until you hit the HC here. But you don't. And that's because the magnetization M is greater than the HCI. So this is where M is greater than the HCI, and in this example the M is wait, I've got that the wrong way around. Yeah, no, that's right. And this here, the M is less than the HCI. So ideally we would like it to be linear. So we want the, and you'll see why that is more clearly later. We would like this to be a linear all the way along till we hit the B equals 0 line. If it's not, if it comes down if it does this, then it's not following a linear path, and then if you move back up, it won't come back to the same point. Okay. Ideally you'd like a magnet material that has a straight line here. So this would be considered a high grade magnet material. And if the curve doesn't go linearly all the way down, that could be considered a lower grade. So then the recoil line, the point where it comes back up, wouldn't go back to the same point, which is not good. You've got a lower, your magnet material now is lower than it was before. Okay. Okay. So now, but in this case, in this idealized case, I said that M was constant across here for the magnet. But in reality, as well, this is not going to be, the M is not flat as a function of H. It does have some dependence with H. So so now think about if M versus H for the magnet, it's not flat, but it is a function of H along the path here, and then it drops off. Like this. Now an actual magnet material, it wouldn't also have a nice it wouldn't have a nice 90-degree angle here. It would have a curve on there, something like that. So this would be actual. But this is but this is slightly more realistic because it has a it's not completely constant as a function of H. So this here would have some dm over dH gradient. Okay, so then in that case, we could write that then M is a function of H. So we could write that M is equal to that's chi H plus MR, where this here is, I'll call MR. And so this chi here is called the susceptibility. It's a measure of the degree of magnetization to applied field. So now with 3 like this, we could substitute that into 2. So 3 into 2. 2 was B equals mu naught H plus mu naught M. If we substitute 3 into 2, we get out mu naught H plus mu naught H plus MR is equal to mu naught 1 plus psi H plus mu naught M, or we can write that as mu naught mu R H plus BR, where mu R is equal to 1 plus chi, which is the relative permeability. And so that then gives us back 1, which I was discussing. And so this here has the relative permeability in it. In the and over here, this has to be B equals mu naught H plus mu naught M here, right? So in this one here, dB dH is equal to mu naught. Now with the M not being constant, having a slight, it's a slight function of H. Now the BH curve will have a gradient that's equal to mu naught times the relative permeability. Does that make sense? So we can write B H and then B over H equals mu naught mu R, where this is HC and this is BR. Okay? So there's a lot of different magnet materials, and there's an awful lot of different curves you can get. I was trying to help explain how M and B are related, because they often confused me when I would look at textbooks. So the BH curve, we will be operating. When you look at magnet material and magnetic circuits, you're mostly interested in the BH curve in this second quadrant here, or fourth quadrant if you second quadrant, or left top quadrant, because that's where you're going to be normally operating, because you're going to have you're going to be applying a current that will be trying to oppose the magnet direction, because you want to interact with the magnets. So for example, in a rotary machine, you'll have magnets on the rotor, and then the currents will be excited on the stator, and they will be interacting with the magnets, and often in a way to oppose the magnetization field. So then the question is, where are we operating? If we have this BH curve here for the magnet, where will we be operating when we have the winding excitation? So I'll talk about that in a minute. But before we just start, let me just show you a couple of BH curves. So for example, this is 3 different BH curves. So if we have BR, and well, actually I'm going to show 4 different ones. So BR and H, and so this, I'm going to put this, let me see if I can do this somewhat to scale. 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, and then this here, 200, 400, 600, 800, 1,000. This is all negative. This is H. So now, if we look at a Hitachi neodymium magnet that has a BH curve that looks something like this. So this is from the data sheet. You can look it up if you want. Hitachi NMX 48. That's a neodymium iron boron magnet. That's a straight line. If it doesn't look like a straight line, that's distortion in the camera. Okay, and then we could look at samarium cobalt, which is another type of magnet material, and that is that's about like here. So this is a so that would be, this would be 48 is one of the higher grades. I think they can go up to 52 or 54 at the highest grade. The number denotes higher grade numbers, and they have different notation for different manufacturers in front of the or behind the number, which denotes different temperature characteristics usually. So it can handle different temperature different temperature levels before it will start to demagnetize. So this one here I took as it's a samarium cobalt Recoma 25, and that's from Arnold Magnetics. So samarium cobalt is more expensive than the neodymium iron boron magnets, but it can handle higher temperatures. So if you really want to have really high temperatures in the machine, you have to think about using samarium cobalt, but it's significantly more expensive. And then ferrites are cheap but not so good. They're used in a lot of cheap toys and permanent magnet devices that are low performance. So this is a ferrite, and this one is also from Hitachi. This is NMF5. These were the names a few years ago. So you can see a big difference in the BH curves. And then the last one, our last type of magnet material, it's not used that much though, is Alnico. And the Alnico BH curve looks pretty disastrous. It looks something like this. Like that. So this one, you can see what I was talking about. It's not linear. Not going to go along like that. You start applying some field from the windings into the magnet, it's going to demagnetize. So it's not very. It can't hold the field very much. So it's not very useful if you want to interact with the magnets with windings, because you're going to easily demagnetize them. So this is Alnico. This is also Hitachi. It's a good advertisement for Hitachi. PMC1B. I bought some Hitachi ferrite magnets a while back. I think that's why I was using all of this. So what really revolutionized things was the discovery of the neodymium iron boron magnets in the late 80s, which they were cheaper, than the samarium cobalt, and they have much higher performance. And these are used extensively in the Prius car and in the Chevy Volt, and the hybrids for Honda. But Tesla doesn't use them. They use an induction machine at the moment. So with with this material, that opened up a whole new realm of possibilities. Okay, I'll stop there and I'll carry on in a minute.